So I'm going to go ahead and start with just another quick review of inductance, inductive reactance, and impedance, just because it is important, and I know it's a topic that a lot of students, you guys don't have a super strong grasp with, because when we get into some of this stuff is pretty, it's a little bit harder to visualize, getting into vector sums and that kind of thing. So just a quick reminder is, we're looking at, with eddy current testing, we're looking at a change in impedance in the coil, okay? And it can be the same when we get to probes and that kind of thing. It can be one coil that is providing the magnetizing current, as well as then the tester is looking at a change in that coil. It can also be, we sometimes have multiple coils where one is called a driver. That's the one that induces the eddy currents. And then we have a separate coil that's called a pickup that is going to be affected by them. But at the end of the day, the display, the tester is kind of handling what type of a probe it is. So remember, with inductance, when we run current through a coil, a magnetic field builds up, and that magnetic field is going to oppose the flow of current. And that's going to, you can think about it like happening immediately time-wise, right? It's going to act like resistance, like you would have in a resistor. And then the other thing that's going to happen is that magnetic field that's causing the inductance in the first place, when it's near anything metal, it's going to also create currents in that material. And those currents in the material are going to then act back on the coil again. And those currents are the eddy currents. That is the basis for eddy current testing. Okay. And that, because of the differences in where the magnetization is occurring, or where the currents are forming, right? There's a current through the wire in the coil being driven by your tester. There's a separate eddy current in the part. That one's going to be 90 degrees out of phase. Or if you look at a phase over time, it's going to be offset by 1/4 of the phase time. Okay, so we have 60 hertz in the US, 60 cycles per second, right? The testers we're using are going to be running in the kilohertz or megahertz range. So it's going to offset that current by 1/4 of 1 megahertz or 1 kilohertz, or whatever our frequency is, one cycle. And when you put those together, when you take the vector sum of those, you get impedance. Both of these, inductance and inductive reactance, are affected by essentially the conductive materials, conductive, not necessarily magnetic, but conductive materials that are in proximity to the coil. So when you bring your probe near a part, it's going to affect both the inductance in the coil itself and the induced reactance, inductive reactance, that takes place and causes a change in those. And so any change in that material is going to change how it's affecting these two items, inductance, and inductive reactance. But at any time, the tester is then, seeing that as an impedance, a change in impedance. So what does that look like on a diagram? So, well, the impedance is that total resistance that the inductive circuit is experiencing because of that induction coil. And it's that vector sum. And if you need a reminder, here's what a vector sum kind of looks like. So we have, if we put inductive reactance on one axis, and we put the resistance or impedance, the inductive reactance and the inductance on the two things. So inductance can be thought of as resistance. It works like a resistor, but it's due to the electric field, okay? So this down here at the bottom is your inductance, essentially. You have your inductive reactance. And this one, they just happen to be, inductive reactance happens to be vertical, and inductive reactance happens to be vertical, and inductance happens to be horizontal, okay? But this can be rotated any direction on our display. But when you add those together, the vector sum, you get the impedance. And so our display is going to show essentially where the tip of that arrow falls on our display. it's going to draw a little point right there. So here's just kind of that visual. So here is the current and voltage are in phase, okay? This is going to be reduced by the inductance or the resistance that's in the coil itself. So as the inductance goes up, this will get smaller or larger. The inductive reactance is going to be out of phase. So this original voltage, now we're just showing inductive reactance is I sub L here. And that's pulled by that, that inductive reactance is formed by those eddy currents acting back on the coil. And when you sum it all together, you get that impedance, that, change in impedance. So it's known as it's an XY plane because of the 90 degrees out of phase. And the resistance vector, again, is going one direction, not necessarily vertical or horizontal. The inductive reactance is going the other direction. Okay, and our screen on our display, here's what the actual display looks like. And these are 3 different flaws. This is what's called the origin. Then you got your 3 flaws. This probe was moved across 3, say, cracks. This looks like a surface crack indication. Actually, I know it is because I took the picture. But this screen can be rotated. So I can't tell you by looking at this which direction is inductive reactance. I can't tell you which direction is resistance or induction. And I can't tell you which direction the vector sum ultimately is. But what'll happen is that changes as the impedance changes. Over time, this point moves around on the screen. And so our screen is set up where it, as the impedance changes, it draws dots at each point in time and basically creates these lines. It works almost like an Etch-a-Sketch. You can kind of think of it like that, as like drawing dots of a line. So this is the screen shown, and the lines you see there have traced the path of that changing impedance vector sum over time. Okay. Now, if you leave the probe in one spot and nothing changes, the little point doesn't move. It just draws a little dot. If you move it across things and it causes changes, you can see it. Another way to look at this is we can look at kind of the magnetic theory behind it. And this kind of shows how eddy currents can affect things in physical form. Okay. So if we look at a picture of what's happening in our test piece now, instead of those fixed magnets like in the videos there, here is our eddy current coil, our eddy current tester coil, which is going to create a magnetic field. That magnetic field is going to react with our conductive material, and it's going to create eddy currents across the surface, near the surface of the material. So remember, early in the lecture, I talked about the fact that this is for finding surface or near surface flaws. Okay, the eddy currents don't penetrate that far into the material. So it's good for finding surface and near surface flaws. It can be used for finding corrosion in thin pieces of material like aluminum skin sheet metal. Okay, but it can't be used to find, a crack like deep down inside of, at the other end of a wing spar. If you only have access in the gear bay area, you can't find a crack out near the wing tip or something like that without scanning out in that area. So the AC coil produces that magnetic field. It forms, it collapses, it forms again the opposite direction, it collapses, forms again, the original direction collapses, right? So it's a changing magnetic field. That changing magnetic field, again, these probes are typically run somewhere in the kilohertz, thousands and hundreds of kilohertz, hundreds of thousands of cycles per second, or the megahertz ranges, so millions of cycles per second, right? And that's creating that current flow in the material. And then the next step then is that, those individual eddy currents that formed, they are gonna form little magnetic fields of their own, shown in blue here. Okay. And those magnetic fields, because you can see the coil's magnetic field here is oriented vertically, the eddy currents are oriented horizontally. That's what produces that inductance on there, inductive reactance on the coil. That's 90 degrees to the original direction, right? Because remember, we learned right-hand rule, if this, this is going to be out of phase with the original coil, the current it's going to cause back in the coil. Okay. And so remember, as I said, as we move our part, you can think of here we have, resistance is induction, okay? Resistance and induction mean essentially the same thing for our purposes, okay? And then inductive reactance, a change in that material, right? A change in this material here is going to affect both of those things. Because remember, we can change the inductance of the coil alone by putting it near metal, right? We can you've seen like transformer windings that have an iron core in them, or some of them are hollow, right? Did you talk about that in electrical? No. Okay, so you can get different induction, or you can change the induction, which is basically the resistance of this coil, based on whether it's near metal or not near metal. So when you have like I said, coils and transformers or other devices where we're not really worried about the eddy currents, some of them, that wire might be wound around a piece of aluminum, a non-ferrous material, but still conductive. Some of them may be wound, the same coil could be wound around an iron bar, or that same coil could be wound around basically a little cardboard tube, which creates what's called an air-loaded coil. And all three of those coils, even if they have the same diameter wire, the same length of wire, the same number of turns, they're each going to have a different impedance or reactance based on, or resistance, impedance or resistance, based on the fact that they have different materials in the coil, near the coil or in the core of the coil. And so the same thing's going to happen when we put that here. It's going to change the impedance, so the inductance, the resistance of the coil. Okay. Now, at the same time, when there's a change in the material, that's also going to change and disrupt these eddy currents down here. And remember, the eddy currents are also forming a magnetic field that's affecting the coil. And so that's the change in inductive reactance. And so as we move our probe around a piece of material, both the resistance, known as induction, and the inductive reactance are going to change if anything about that material changes. And it can be incredibly small changes. It can be micro cracking that you cannot see. And that will disrupt the eddy currents and disrupt the amount of material in front of the coil. And that will change the impedance. It will cause an impedance shift. It can be the geometry of the part changing. It can be that corrosion on the backside that causes the material to get thinner, right? A thin piece of sheet metal to get thinner. All of those things are changing both the resistance of the coil and the inductive reactance of the coil, and together that changes the overall impedance. And so we're looking for, when we're performing eddy current inspection, we're looking for a change in the impedance in order to determine whether something changed about the material. That's what our tester can tell us. Something changed about the material. That's all it tells us. But if we want to know whether that's a crack or corrosion or something else, we need to have a standard. We need to run our probe across a known item, see how it reacts, and then we go run it across our test item. And if it reacts the same way, then we know we have the same type of a flaw. So some things we got, some of the vocab that we need to keep in mind or know in order to kind of understand what's going on when we're talking about this. So current density, this is the amount of eddy currents in a given area. How strong, how many of those little current things form in the material? Okay. And the current density ultimately is going to affect our sensitivity and accuracy of the test. We need to have a certain amount of eddy currents forming. But if the eddy currents are actually too strong, they can actually block our ability to see in the material, which if we're looking for surface cracks, that's not a big deal. But if we're looking for corrosion on the backside, we can't, we need to make sure that our eddy currents aren't so dense, we don't have such a high density that we can't pick up flaws deeper in the material. So the current tends to concentrate at the surface and material adjacent to the probe. That means you have like a 90-degree corner, you're going to get a different indication than if you're on a flat piece of metal. So this is a calibration block or a test block. And just for pointing purposes, I'll get out a probe, because that's easier than trying to use a pen or a finger. Where's the probe I want? There it is. So, what I'll get here on this thin flange is going to be different than what I'll get on the thicker part. And what I'll get on the very edge of the flange is going to be different than what I'll get near the side, because this vertical section chunk of metal is going to affect my probe. This thing is freezing. It's been in my car overnight. Not hold it too much. And then on top, we've got all kinds of different things. We have different materials. We have simulated cracks. We have bolt holes with simulated cracks. So we've got different probes for all these different types of areas. Okay? So, but what I'm getting at is that the material below, directly in front of, as well as adjacent to that, is going to have an effect on the little tiny coil that's in the end of this probe right here. Probes come in different shape sizes. We'll look at them here a little bit later. Whoops, come back. So that current tends to be at the surface. The current density decreases exponentially as you get down into the part. And what this results in is something called skin effect. When those eddy currents form at the surface, the magnetic field that they give off blocks our ability to detect deeper in the part. And so we get that kind of a skin layer of eddy currents that prevents us from being able to see deeper in the part. There are ways to get around that. We'll look at that. Okay. But with a given setup, how far we're able to look, that's known as the depth of penetration. So how deep into a material are we able to see a feature, a flaw, or some kind of, pick up something that's going to cause an indication. So that depth is proportional, the density of the eddy currents, right, is basically inversely proportional to the depth of penetration. If you have really strong eddy currents at the surface, you get skin effect, you're not going to be able to inspect very deep into the material. If you have a less dense layer of eddy currents at the surface, you're going to be able to get a greater depth of penetration to see flaws further down. And with any given set of settings and probe combination and frequency and everything else, we can calculate what's known as a standard depth of penetration. That is, where is essentially, as you go in, the strength of this field is going to fall off exponentially. Okay. And the point where, so here is a depth and a strength curve. The point where our strength has been reduced by 37%. Anything above that, so anything up here, we have a strong enough view, so to speak, that we can say we can effectively find flaws. Anything below that 37%, because our strength drops off so much, we can't effectively find what we're looking for. So we can, materials engineers and electrical engineers, the people that are going to design these tests, they're going to calculate what that standard depth of penetration is based on, how thick is the material and how deep do we have to look for a flaw. If we're looking for corrosion on the backside of a 50 thousandths piece of sheet metal, and the standard depth of penetration is only 20 thousandths, we're going to have to change something to be able to see the full 50 thousandths, right? So below that, the signal drops off too much where it's insufficient for effective testing. That's this area here where the signal strength gets too low. Okay. You can kind of see it creates kind of a cone in the material where the eddy currents form. they've actually done, you can use a visual magnetometer to look at how this occurs. So here is the coil, kind of it shows what the coil looks like on a part. And you can see that cone kind of forms. Now, because the coil's circular, you actually kind of get two areas with this coil here, right? So the strongest part there is kind of in yellow, and then it drops off to red, eventually kind of blue and purple and black, right? This is looking at that strength of magnetic field. Now, I don't know, with this setup, and the color coding they put on there, I don't know what the standard depth of penetration is here, but I would imagine it's somewhere around that border between the yellow and red. Okay. So even though that magnetism goes much further, those eddy currents, that magnetism and eddy currents form much further into the part. In this case, you would only be able to look at that very top portion. So here's what that's affected by. So we have our coil operating frequency. Remember, I told you these are going to operate in the kilohertz range, megahertz range, right? Like this probe here, for instance, this probe is designed to work from 50 to 500 kilohertz. Okay. Some of our bigger probes, I don't remember what this one does. I'd have to. This one is, actually, this one's down into the hertz range. This is 10 hertz to 1 kilohertz. Okay, so different probes are designed for different ranges. But the coil operating frequency is going to play a role. The material's conductivity or resistivity, right? So, aluminum versus copper versus steel, right? They have different electrical conductivities or resistance levels, right? Those are inverse of one another. Okay. And then the material's magnetic permeability. Remember, because something's conductive doesn't mean that it's magnetically permeable, right? Iron and carbon or low carbon steel can form magnetic fields a lot easier, stronger magnetic fields than something like aluminum or copper, which really don't have, don't create strong magnetic fields, strong permanent magnetic fields, right? So of these three, we can only change one. Which one is that? For a given material, what can we adjust? The coil operating frequency. What frequency do we send down to our coil? We can't do anything to change. If we're checking the skin for cracks on an aircraft, that's made of aluminum, sheetman aluminum, we can't do anything to change the conductivity or the magnetic permeability of that material. It's based on the alloy, the aluminum, and then whatever alloying agents are in it that go all the way back to when that material was manufactured. So you can see here, frequency is on the bottom of our equation. So if I want to look at surface flaws, things that are close, do I need a high depth of penetration or a low depth of penetration? Low. I don't need that signal to penetrate very far in the part. So if I want a low depth of penetration, would I run a relatively higher or relatively lower frequency through my probe? If frequency is on the bottom, the higher the number, the bigger the number on the bottom, the smaller the resultant depth of penetration is going to be. If I want to look for corrosion on the backside of a material, what would I have to do? What kind of a frequency relative to what we were talking about before would I need to use? A lower frequency. I reduce my frequency. That reduces the amount of skin effect, the amount of currents forming right at the surface, and it allows that probe to get a greater depth of penetration. And so something like that little pencil probe I was holding up is designed for surface flaws. This operates at high frequency, again, 50 to 500 kilohertz, 50 to 500,000 hertz. We have some bigger, this big coil probe that's 100 hertz to 1 kilohertz, lower frequency. This is designed for doing like bolts and rods, and you want to be able to look through the entire bolt to make sure you don't have any cracks forming at the center of it. Right, so you can run a bolt through this. to try to find internal cracking. A lot of times bolts in certain stress situations, cracks form from the inside out. So you'll see cracks in the center before you see them out near the surface. Okay. Once they hit the surface, that's the bolt failing. So here's what that looks like. So on the left here, we have a high frequency, same probe, same material. We're using a higher frequency. It's going to have less penetration, but what it is going to do is it's going to be able to find smaller flaws. So the higher the frequency, the more sensitive our test is. But we're not going to find the flaws deeper in the part. We're going to find smaller flaws near the surface. If we need to find those deeper flaws, corrosion usually is visible, right? In most cases, before it becomes so bad that it causes a failure, usually it's visible. Cracks oftentimes can be so small they're not visible at the surface. We may be able to, the corrosion we're trying to find in like a lap splice using eddy current testing, if we were to pull that apart, we'd probably be able to see it without a problem. But we don't want to pull it apart. That's why we're using an eddy current tester to find it, because we don't want to drill out 10,000 rivets holding the skin splices together in order to do an inspection and then have to put all the rivets back in and have to repaint. Probably reinstall the interior because you had to remove the interior to buck the inside of them, right? So low frequency can give us greater penetration, but it's going to be less sensitive. The flaws we're going to find are bigger, but it can be used to find those flaws where the size isn't nearly as critical. They're less size critical. It's okay if we find them when they get bigger. They're not going to cause a failure when they're micro cracks. Skin cracking, rivet hole cracking can cause failures at the micro crack level. They can start to grow very, very quickly when a plane pressurizes. And then you end up with the Aloha Airlines flight where the top of the fuselage peeled off. So here's just kind of a table. You get your, things like conductivity, resistivity, or permeability, which is the next chart. These are set based on the material. These are determined, you're getting into materials engineering to determine this stuff. Okay, so for our purposes, most of the time, even if you are a level 3, if you're level 3 qualified in performing eddy current testing, especially if you didn't come from a material science background, you're probably going to be looking up these properties in tables most of the time. This stuff is well researched, well known. There's no point in like spending huge amounts of time and money figuring it out yourself when somebody probably already knows, a manufacturer that makes the alloy already knows these items. You can get it from them. So if you are trying to design a test, you can look up tables, electrical resistivity and conductivity of selected materials. This is from ASNT, American Society of Non-Destructive Tests. They put out a lot of these. ASTM, American Society of Technical Manufacturing. Automotive, what's the big automotive one? ASE is mechanics, right? What's that? The UAW is the big union in the automotive industry. But, so for a given frequency, if we go back to that equation, if we have high resistivity, with a given frequency, we're going to have greater penetration, right? High resistivity. Right? We have low resistivity, we have less penetration. But again, we can't change this. This is just based on the material. Permeability. How strong, when we put a material in the presence of a magnetizing force, how strong of a magnetic field forms. You can see iron, right? Iron magnetizes very easily. You don't need a ton of force to get it to magnetize. You can see these are in combination with air. It's actually harder to magnetize copper, lead, and silver than it is to magnetize the air around us. Now, air can also depend on moisture content and, all kinds of things like that. But, air is basically considered 1. But you can see there's a lot of stuff that's basically 1. Manganese you can almost say is basically one. Titanium, aluminum, oxygen, air, copper, lead, silver, those are all basically one on this scale, where iron is 180,000 times easier to magnetize. Nickel's 600 times easier to magnetize. Cobalt's 250 times easier. So why, so if we have high permeability, something like iron, nickel, or cobalt, we get less depth of penetration. If we have low permeability, we can get a greater depth of penetration. Why is that? What prevents what blocks the depth of penetration? So those eddy currents that form and create magnetic fields in the part, that magnetic field is what's blocking our ability to detect deeper in the material. It's part of that skin effect that occurs. So you're going to get a much stronger skin effect in something like iron than you will in anything from manganese down. Right? So iron is extremely difficult with eddy current testing to do anything besides surface crack checks. Even nickel and cobalt are rather difficult to do any kind of internal checking. So you're probably not really going to do backside corrosion on a piece of iron bar stock. But with something like aluminum, relatively speaking, it's much, much easier than iron. So, as I said, the primary, most of the time we're going to be working with aluminum in particular. We're going to be looking at working in the kilohertz or megahertz range. You can see we do have some probes that go down into the hertz range, right? Like that big coil probe there. But because we're using this primarily on aluminum parts, titanium parts, magnesium parts in aviation, we're going to be working with those higher frequencies. So selection of frequency is always a compromise. Remember, high frequency has a greater sensitivity, low frequency has a lower sensitivity. But your high sensitivity is low depth of penetration, low sensitivity, high depth of penetration. So it's a balancing act. How big of a flaw, how small of a flaw do we need to find? And can we keep the frequency, can we make the frequency high enough to find it at the depth we need to? So, again, you're looking at that conductivity, resistivity, magnetic permeability when you're deciding what kind of a test you're going to set up. We want to reach the expected flaw, but there's really no point in reaching way beyond the expected flaw because our sensitivity is going to drop if we do that. And so that's why we have different probes that run at different frequencies for surface cracks than we do for finding something like backside corrosion. Actually, so we'll look at probes in more detail, but here is a high frequency surface crack probe. Here is a low frequency side corrosion probe. What do you notice about them? The low frequency is bigger. You can run low, the coil size directly correlates to the frequency you're going to run at. So this one may not be readable anymore. I might have to look at my cheat sheet. This is 500 hertz to 30 kilohertz. Right? And then this one, remember, is even bigger. This biggest encircling probe is 100 hertz to 1 kilohertz, right? So you can see lowest frequency, medium frequency, high frequency. Okay. This is for your steel bolts. That's why it's such a big probe. It runs at a very low frequency to try to get that better depth of penetration. In some cases, we may want to look at multiple things at once. And so there's actually what's called multi-frequency testers, where you have a probe set up, and a probe can have more than one coil in it. Okay, the different coil. You need a bigger coil to run a low frequency. You need a smaller coil to run a high frequency. You can have a multi-frequency, multi-coil probe that can, those thousands of times per second, it can swap between high frequency, low frequency, high frequency, low frequency, and it actually can do a surface and a backside corrosion simultaneously. They're not as common, they're much more expensive, and the testers that run them are much more expensive. But they do exist. Actually, this tester can do multi-frequency, but it can only do multi-frequency with a single coil probe. So it's not a great multi-frequency tester. They have to both be within the range of the probe size you've selected. So that gives you increased resolution and depth limit over a single frequency. Okay. So I've already started pulling out the probes. I'm going to show some of the probes, and then next time we'll get into actual setup and that kind of thing. But here's a selection. I've already picked up some of these. So they can be referred to, you'll hear probes referred to often as coils. However, keep in mind, a lot of probes, in fact, majority of probes have more than one coil inside of them. Okay. And so then they come in physical shapes and sizes for different applications, for different purposes, including you can get them custom designed to fit certain features or contours. So a common custom design probe is they make probes for specific wheel rims to check the bead seat area for cracks. So when you take your wheel off the aircraft to get a tire change before they put the new tire on, they run a bead seat probe around to make sure there's no cracks in the bead seat area. So standard shapes, which is what you'll be using, they're kind of generic. First one we have is, these are flat probes. This one's actually flat and spring-loaded. It's got a little spring inside of it. So what that does is when I put it apart and move it around, it helps to keep that coil in contact. Remember, we're trying to find cracks that you can't see. If I just take a probe, like if I have this probe and I wobble it a little bit, I'm going to get an indication. I cannot hold this steady enough to not get some kind of little indication. This one's pretty good. It's got this nice flange. You can hold it nice and tight. Spring holds it against it, but it'll still get a little bit of movement as you move it across the part just from surface roughness. So something like this, these are cracks right here. I can go fine. That's what you saw in the picture where I said this is a crack indication. This probe across some cracks. So there's the actual coil in there. You can see their probes relatively the same size, two different actual size coils or probes. So which one is our higher frequency probe, left or right? Right, high frequency has a smaller coil in it. Left probe is higher or lower frequency. Which one is going to typically be used for near surface, closer to the surface flaws? The right one is going to run a high frequency. It's going to have a lot of higher resolution, but it's going to be limited to limited depth of penetration. So probes can also, in addition to their physical design, they can be shielded in different ways. And that is, we want the eddy currents and we want the signal to form directly in front of the tip of the probe. But remember, a magnetic field likes to spread out to some extent. So we put shielding in some cases to kind of control that, try to keep that in place. The reason for something like that is to limit things like what's called edge effect and interferences. That is, remember I said if I take this probe and I move it across this little narrow flange here, I'm going to get a different indication because of the thick metal here. I'm also going to get a different indication as I get to this edge over here. That's edge effect, right? Because right now, if it's spreading out, part of the eddy current or part of the magnetic field and eddy currents are going off the edge of the part now. And so that'll give a different indication than if I put it in the middle where that won't happen. And then if I put it all the way to the left, my left, you're right, part of those eddy currents and magnetic field are going to form in that vertical portion, that thick piece. And that's going to change how the probe reacts. So by shielding it to keep that more down rather than spreading out, we can get, we get less effect from things like this taller edge, big chunk of metal, or this thin edge on the right when we get edge effect. Nope, you can test it different ways. This one actually has a crack here that you find by going this way. It also has a crack in the end that you find that runs the other direction when you go like that. So you'll test it both ways, but by having a, say your actual part on your aircraft has features similar to this, that way you can see, okay, normal indication here, this is a normal indication as I approach this part, that's a normal indication as I get to the edge, and then when I go across this crack, I get a totally different indication. No, you just move around and you're looking for a change in the, you're looking for that change, that impedance change, impedance shift over time. Okay. Okay, I'm going to go ahead and stop there.